Thanks, Tarek, for a wonderful introduction. So welcome, everyone. So today I'm going to talk about achieving personalization with LSTMs. So I am Ankit. I'm a senior data scientist at Uber AI Labs. So this is the work we did particularly for finance and strategy teams at Uber. So let's begin. So before going further, I just want to highlight that Uber is one of the few Silicon Valley companies which leverages ML for business strategy and finance operation. And rightfully so, because our business is not a very high margin business. So the only way to do better in our jobs is to be very efficient and use ML wherever we can to reduce cost and improve efficiency of the system. So the agenda for today's talk is I'll just briefly introduce forecasting at Uber. We'll formulate the problem, we'll look at modeling and some results. So forecasting is of paramount importance to Uber. So we forecast various things like how many trips we are going to take, how many gross bookings we are going to have, how many drivers are going to come online, and variety of metrics. But forecasting at Uber is little different from other companies you would have seen forecasting in because of primarily two aspects. One, which is quite similar in terms of time horizon. So we forecast from as low as few minutes to as high as a year. So few minutes, you might think of an application that if you are thinking that probably will be undersupplied in one particular part of the town, let's say there is a concert, we might guide drivers to go there so that we can serve more trips. So forecasting helps in that case. Forecasting on a year front is more about how do we assess our business and how do we allocate the budgets that we have to various parts so that we can maximally achieve ROI on that budget. So that is the time horizon part. The second part is obviously space, which you don't generally encounter in many of the cases. So we can forecast on a neighborhood like San Francisco downtown, we can forecast on a city, San Francisco, we can forecast on a country, or probably a mega region also in some case. So that's the brief about the overall forecasting at Uber. Let's look at something which we are mainly going to touch today is trip forecasting at Uber Finance. So for the trip forecasting, let's say that we have two data sets kind of thing, not two data sets, two types of data. One is obviously historical trips of a city. For example, for San Francisco, you have a time series of how many trips we have done in San Francisco. Then there is another data of acquisition spend, which is basically the marketing spend you would have seen for a referral bonus or something else like that on your apps. So that is the money we spend in general to acquire new drivers or riders. In the current setup, what is happening is, so this is more of motivating the problem also. In the current setup, what is happening is, we use these two things. Put a time series model, you can think of a very standard time series model like Arima or others, and we generate a long-term forecast, which is like say 52 weeks out. Now this is obviously, as I said, is useful for if you have to decide how much budget we should allocate in different parts of the company. But what happens is, as soon as you start the year, something or the other happens, like competition raise more money, there is new regulations. So whatever forecast we do kind of have to be reevaluated once you start a new year in that front. So for that purposes, what we need is a short-term rolling forecast also. Let's say we are in February of the year, we should use the data of January to assess our forecast, reevaluate our forecast better. And also, this is a good time in terms of short-term rolling forecast, which is like 1 to 2 weeks, 12 weeks, to reallocate our budget so that we achieve the trip target that we initially set out to, or even more in some cases. However, there is a key link missing in this whole setup, and that is the two spending levers that we have of driver incentives and rider promotions. So when I call driver incentives, is basically something you would have seen on drivers talking about is like if I do 50 trips, I get $100 kind of thing. So that's a monetary incentive I'm talking about. Then there is sometimes a guaranteed surge in which if you drive in this area or take a trip in this area, you'll at least get 1.5x irrespective of what rider pays to you. The rider promotions is basically what you see on your app, like 10% discount, 20% discount, something like that. So we allocate budgets also on driver incentives and driver promotions, and currently they don't make it in any sense to short-term rolling forecast, primarily because we don't see a significant statistical signal from the models that we are using for generating this long-term forecast. And because we are using similar models for long-term and short-term, sometimes it just doesn't work out. So what we have done, and that is the primary goal of this talk, is we looked the problem in a very bottoms-up manner. Rather than saying, oh, let's take a time series of San Francisco and develop a model, why don't we think that, let's say for driver incentive, if I'm able to predict in some sense for each driver on the platform how much trips he is going to take based on what incentives I'm giving him, I can pretty much roll it up to the entire city and see the effect of incentives on my short-term rolling forecast. So we'll mainly talk about this personalized model in today's talk on how we incorporate particularly only driver incentives for this talk or on the short-term rolling forecast. Before going further, just to formalize the business requirement for something like this is first, we want business to do some scenario generation. I don't know if you can see the GIF very clearly, but I'll just explain. So what it tries to do is, like, if I am a stakeholder in finance, I want to see if I put 1 million tomorrow in San Francisco as an incentive budget, how much more trips I can get, right? So that is one scenario generation part. So the business stakeholders can play around with incentive budgets to see which is the right number to put. That's one way. The second is, obviously, if you have a personalized model, you can assess how much deviated you are from the forecast. Let's say you predicted a forecast of, I'll do 1 million trips, but let's say you are at 900K, you want to assess where should I spend my dollars, or which user should I focus on to kind of achieve my trip target of 1 million. So if you have an individualized forecast, you can better assess on which users who are expected to be high engagement were low engagement this time, or which users who are expected to be low engagement have increased their engagement this time. So you can assess the deviation of forecast to something like this. Third one is more of a side effect, I would call, rather than something which is heavily used right now, is once you have a forecast for individual users, you can develop a cohort, and you can sometimes assess product launches through counterfactuals at times when we are not able to do A/B test for some things. So this is what the motivation of the overall problem is, and this is what we are trying to achieve through a personalized model. So yes, so combining insights like this can help Uber adjust its budget in the short term, you can understand. So the next part is, let's see what the problem formulation for something like this would look like, and how we have used modeling in the further parts of the talk. So the functional form, particularly for incentives, if I have to term it mathematically, is we are trying to learn a function g which has inputs of 3 things, I, ft, trips t, to predict capital T. Ft is nothing but, in this case, features from 0 to current time t. Let's say the current time is t. We want features, historical features, and we'll talk about this in a minute. What are the historical features we are talking about? So we have a vector of features till time t. Trips t is basically a vector of trips we have taken, or some driver has taken till time t. The capital I is budgeted incentive spend vector for next n weeks. Now this is a little different. Like in usual machine learning, you cannot peek ahead on the data that you're going to expect, but you always can use only historical data. But this case is a little different, because if stakeholders want to play around with the budgets and see what the effect would look like, they have to be incorporated in the model in some sense or the other, right? They need to say that, oh, this is my budget for next 6 weeks, for example, how much more trips we can expect in 1 to 6 weeks. So that is why we have a look ahead in this case, or peek ahead budgeted data that we use for this model. And the T, capital T, is the trips for the next n weeks. Now n can be 1 to 12, depending on the use case, people use differently. So that is the functional form. Now let's look at how we achieve this functional form through modeling. using LSTMs. So the data in this case is threefold. The features I was talking about is, for each driver you can imagine 3 types of data. One is static, like which city the driver belongs to, or majorly he drives, what is the acquisition channel, what is the acquired month, something which is not confidential and very static and doesn't change once the driver is on board on the platform. Then there are behavioral features in which you can think of how many trips he has done, how many supply hours he has done, how many search trips he has taken, how many cache trips he has taken, particularly in India, and then how much earnings he has had, and how many accepts, how many rejects, etc., etc. Like you can think of many more. And the third is incentives. As I mentioned, we have many kinds of incentives, but few of the major ones are, we call it DXGY, like do 50 trips, get $100 style. Guaranteed search, in which if you drive in a particular part of San Francisco, you get 1.5x. Then there are others like per trip incentives, and sometimes more variants of these things also. And finally, we have historical data of incentives, and we have look ahead budgeted incentives for the future that we use. So overall, the data granularity is like, you can think of each row of data set corresponds to weekly features of a driver and n target variables, because we are predicting for next n weeks. Obviously, this we'll have to convert to sequences when we do LSTM modeling, and we'll see that in a minute. So modeling parameters, before going to the exact model that we have used, modeling parameters is, model granularity is separate model for each city, because in general when you try to model completely for, let's say, US, there are so many variations within the cities itself, so it's better to model on a per city basis, and that's what the results we also got, better results for per city model. Evaluation metric, now there are 2 evaluation metrics in this case. One is mean absolute error, like how much on an average basis the driver, we predicted the trips of a driver and how much we are off. Basically, you can think of, if on an average driver is taking 3 trips, if I am predicting 4, MA is 1. However, there is an issue with something like MAE metric. One of the major issue is you might, if you just focus on MAEs, you might end up selecting a biased model. How do I explain this? Let's say I have MAE of 1 in my model, and I have 1 million drivers. So MAE of 1 means that there is a possibility that I can overpredict by 1 trip for each and every driver on the platform. Now, the MAE looks good of 1, but at the same time, when you aggregate all the drivers, you have 1 million trips off from the actuals. So you need to see that your model is not biased by using something like we use MAPE, which is mean absolute percentage error at city level, to check if the model is biased or not. The third is baseline. So as in machine learning, we have to construct an appropriate baseline, which is pretty easy to kind of evaluate. So for the baseline, we took whatever driver did last week, let's do a flat line and extend this for next n weeks. Okay, so it's very easy, and turns out it's a very good baseline in general. We had to do a lot of modeling to kind of beat that baseline sometimes, and just take the last week's data and extend it for the next n weeks. So the best model we got is LSTMs with 0 inflated Poisson loss, and I'll explain these 2 things next. Before going further, I think most of the people are aware in the crowd, but just to highlight that LSTMs versus classical ML models. So in general, deep learning models and also LSTMs are very data hungry, and because they are data hungry, we need to feed in more data to kind of get any good signal from them. So that serves very well, because in this case we already had a lot of data, so that was not an issue. Because LSTM models are sequential, time dependencies are very well captured, and this is more of a forecasting problem, so we needed time dependencies. And then secondly, LSTMs are generally good in modeling hidden nonlinear interactions, and we had a lot of them because human behavior is complex, and we need some modeling to kind of do nonlinear interactions. Okay, let's talk about zero inflated Poisson loss. So if you see our y variable, the weekly trips, it has following two properties. One, because we are predicting trips, it's a count data, so it's non-negative. And one obvious way to model count data is Poisson distribution. However, there is another angle to our y variable, is there are a lot of structural zeros in the system. How? For example, if you are trying to predict for a driver, and you might observe that the driver just doesn't work for 1 week and then come back on the platform. And there are several reasons for it. Driver is on vacation, he has another part-time job, he just doesn't feel like working for a week. So you have a time series for a driver, it goes to 0 and then it again comes back. So a lot of structural zeros like this in the system, which if you just think from a Poisson perspective doesn't make sense, because Poisson is generally not very good at modeling those structural zeros in the system. So another way to understand the same thing is something like this. Not sure if you can see the axis titles, but I'll just explain. So this graph shows a scaled trips, histogram of scaled trips by driver in a city. So on the x-axis you have scaled. I cannot disclose the exact amount of trips. So the x-axis is scaled, and there are bins in the x-axis, and the y-axis is fraction of drivers in a city in a week that did that many amount of trips. And you can see that many of the drivers just did 0 trips, and not that all those drivers were churned, they came back next week, many of them. Some of them were churned, but they came back next week. So there is always this thing that driver just stops working for a week or two and then comes back on the platform. So that was the one major issue we faced when we were starting to modeling this, and that's why we decided to go with a loss of zero inflated Poisson. So what zero inflated Poisson does, it tries to introduce another parameter pi other than lambda, that is a usual Poisson parameter, which tries to model structural zeros. So pi is, you can think of nothing but a probability of something like a driver will work or not. Like think of it as a threshold, let's say it's 0.5. Below 0.5 driver will not work, so you don't have to take care of what Poisson is predicting in terms of number of trips. If it is 0.5 and above, then we see what number of trips we can get through a Poisson distribution. So this kind of modeling takes care of the structural zeros that we have in the system. Now let's look at model architecture. So it's pretty involved. We'll go from bottoms up in this case, and I'll try to explain each block one by one. So the first one is FT, which is the feature of a driver at time t in this case. So static behavior or the previous historical incentives data that we have observed for a particular driver is there in this FT. Think of it as a vectors that will feed into one by one into LSTMs. What these feature vectors feed into LSTM1, and what LSTM1 is trying to do is, based on all the history of a particular driver, give me an embedding that I can use further. Okay. So in this case, so LSTM1 is pretty much trying to generate an embedding for a driver, and so the output is feature embeddings per driver. Now what we do is we use these embeddings along with another data, which is IT plus 1 to IT plus n, which is the budgeted incentives I talked about earlier. So we have feature embeddings and you have budgeted incentives. You push both of them in LSTM2. Now, for LSTM2, you might ask, why do we need an LSTM itself in this case for second LSTM? First LSTM, we understand it's basically time series, you sequentially model, you need the LSTM, but for why LSTM2? So initially we didn't try LSTM2 in our modeling. The reason we required it is because we observed that incentives don't always have an instantaneous effect. Like obviously if you give somebody an incentive, do 10 trips in the next 1 day, I'll give you $50 kind of thing, you can incentivize people to drive, but that leads to sometimes a change in behavior also of drivers, so they continue working for a long period of time. And so also sometimes the structure of incentive is not that they finish always in a week, sometimes it extends also. So we needed something to capture the lag effect of incentives in our model. And for capturing that lag effect is basically again sequential. So the one easiest way to model is just put an LSTM there and see how it performs. So in this case, what is happening, the output of LSTM2 here is feature embeddings for a given forecasting period, right? So if you are predicting, let's say 6 weeks out, this figure is for 6 weeks. If you are predicting 6 weeks out, the output of LSTMs is like feature embeddings per week, per forecasting week. Now you have got an embedding which incorporates both the historical data and budgeted incentives of the future. We want to map that to the distribution that we talked about, which is zero inflated Poisson, right? So we use a fully connected layer here, which basically takes the embeddings of a driver and map it to two values, lambda and pi. Now the lambda, so the lambda and pi in this case are the parameters of zero inflated Poisson. The good part about this is that now not only you can generate the point prediction of a particular driver, but also you can generate the distribution of trips somebody is going to take. Now this is very powerful in the sense that you can use this distribution per driver per week of forecasting to quantify uncertainty in your prediction, into your predictions also. So because forecasting is always not right, it's good to quantify uncertainty to kind of make your budget smarter. So by predicting distribution rather than a point value, we are able to quantify the uncertainty also in the predictions. And finally, to obtain y1 or y1 to yn, which is the final trip prediction, there are several ways to go from lambda pi to y1. One is we take the mean of the distribution. However, if you are not shown a figure here, but if you see the zero inflated Poisson, because of structural zeros in the system, it is a bimodal distribution. And when you have bimodal distributions, you cannot directly take the mean of that distribution, because mean will fall into between two modes where the probability is just very low in general. So what do you do? And as I mentioned, we were optimizing on MAE, that was our eventual metric, to see one good way is to just choose a median of the distribution and use it and see how it performs. Another way could be, I'll do a cross validation to figure out the pi threshold and then choose directly the lambda value. So if the driver is above a threshold pi, I'll choose the final Poisson parameter as a trip prediction or mean of Poisson distribution. So there are several ways we tried. We went ahead finally with median because that worked decently well for our case. So this is the overall model architecture. So it overall, in summary, it involves two LSTMs, one to generate feature embeddings, second to capture the incentive budgeted effects, and then we predict not a point value but a distribution of each driver on each forecasting period, and somehow convert it to the final trip number that we want. And as a side effect, we get some uncertainties also that business can use. Okay, so let's talk about results. I think this will be short. So mean absolute error comparison. So there are two graphs, city A, city B. I'll not name the cities. And there are 6 forecasting weeks in this case, so 1 to 6. On the y-axis, there is actual MAE, mean absolute error. And there are 3 curves here. One is blue, which is the benchmark or the baseline I talked about, which is just producing flat line. As you see, it's not very bad. It is sometimes better than, for these 2 cities, it works sometimes better than the random forest. I don't know why right now, but it worked, it just gave the result better. And the third line, which is the green line, is the zip model that I talked about, the LSTM zip model that I talked about. And you can see for both of these cities, MAE is around, like for first city is around 5 and the second city is around 7, but it is a substantial improvement. And particularly for city B, if you see, if you go far out 6 weeks, obviously the trips he has done for 6 6 weeks before obviously should not be able to predict what he is going to do 6 weeks out. So for those things, like LSTM models are kind of performing very well. It's like almost a 30% improvement on whatever we have. The second is, now this is one way to evaluate. The second is we wanted to see whether the model is biased or not, which is the mean absolute percentage error comparison. Again, there are same two cities, city A, city B, 3 curves, forecast weeks is 1 to 6, and the y-axis is MAPE. In this case, the only difference is the benchmark I'm talking about is different. The benchmark is the existing time series model for long-term forecast that we have used. So we wanted to compare how that benchmark compares with what we are predicting overall, and you can see that the neural network models, which is the green line, at par or even better than what we have currently. So this also validates it's performing to similar to benchmark, indicating neural network model is not biased. We have a good MAE overall. We have incorporated the incentive budget into the system, and we have a model that probably can business stakeholders can play around now. Another graph that we should see is this one. So this one on the x-axis it has incentive multiplier. I'll explain this. And on the y-axis you have average trips per driver. So what does incentive multiplier means? By the way, this is on the test data. So we knew what actually budgeted incentive was in historically. So incentive multiplier shows that when value is 1, it is the actual incentive that we served that week. Okay. Multiplier means if I change the incentives to 2x, 3x, 0x, what are the changes in my trips on average trips per driver front. And you can see, first of all, the 6 weeks, the 6 curves correspond to the different 6 weeks that we are talking about. And you can see that all of them follow a concave curve. What does it mean? It means first interpretation is that incentive works. Okay. So if you do it 0, your obviously trips reduces. So incentive definitely works. That's a validation, number 1. Number 2 is incentives cannot work forever, because time is limited. Somebody can only drive 24 hours a day. He cannot drive 25 hours a day. So even if you give $1 million, he can only do so many trips, kind of thing. So this also validates that it is concaving down. So if you basically keep on increasing incentive, the value of additional trips or the number of additional trips you might get is just not significant. So it validates that part. The third observation is, and you see that the 6 curves follow a trend in terms of week 1 is above, week 6 is below. And the reason for that is because the way this graph was generated is that basically whatever existing users we have till, let's say, time t, till time t plus 6, some of the users will churn out. Some of the new users will join the platform, but that is not what is captured here. What we are predicting is whatever the existing users we had, how much trips they can do further. So obviously, first week less people will churn out. 6th week more people would have churned out. So if I keep the number of drivers to be same and the denominator is same, the average trips will go on reducing, because some people will just take 0 trips because they have churned out of the system. So you will see the clear trend that week 1 is above and week 6 is the lowest. So this also validates that model is somewhat consistent, because sometimes in deep learning models you don't know, some results are very not intuitive enough, but in this case we have validated that first incentive works. Second, there is obviously a churn pattern that we can see, and third is incentives cannot help above a limit. So I think these are the primary 3 observations. And overall, right now, the business, we have deployed this model in production. We are trying to scale this up to multiple cities. For few cities, it's live, and business is trying to use this right now to decide incentive budgets on a short term, and it has been a very good help overall for them to make decisions on how to prioritize incentives. The similar model on promotions is on the cards on rider promotions, but that is not the point of discussion today. I think I finished it way earlier. So I'll open for questions. Sorry, go ahead.
On your city A and B, city B performed a lot better versus the benchmark. Without revealing the city names, can you talk a little bit about maybe any differences between the two cities? Was one mature market versus a new market, big city, small city? Why did you see so much better?
So the question is, when I show the city A and city B, I think you're talking about this one. So city A performed better than city B, and why that might be so. So I don't have 100% clear answer, but I'll say from my observation is that one is obviously it depends which stage city is in, whether it's growth phase, saturation phase. How many? I think another part it depends on is how many part-time drivers versus full-time drivers, right? If you have more full-time drivers, it's easier to predict for them because their livelihood depends on that, right? But if you have part-time drivers, the structural zeros I talked about are just sometimes present, and you cannot predict. They are so random. So some of the times you are not able to get the MAE that you want for some of the cities. So I think part-time versus full-time drivers is a major distinction between these two cities.
I wanted to ask about the role of external data. I know Uber obviously collects a lot of data, but I'm curious what other data sources you use. You mentioned like if there's a concert, you'll move cars there. So is that something you're automatically pulling? I'm just curious what that pipeline looks like.
So the question is, how do we use external data in this case, or if at all we use it, like I mentioned about concert, do we use any kind of data like that? So for this case, no. Because it is not very, very short term. It is little long term, I would say, from a concert kind of setting. So many things average out over that time period. So for this, we don't, but I think there are other applications inside Uber of forecasting where people use a lot of external data through APIs and everything else, weather APIs, events APIs, and others to kind of figure out what are the external things that are happening.
A lot of this, I think, assumes a fixed number of drivers, right? So what about promotions to increase the number of drivers?
So the question is, this assumes fixed number of drivers. How do we scale this to a new number of drivers? So the question is right in terms of we do. So the basic prediction of this model is on the existing drivers on the platform. And obviously new drivers will join the platform, and you cannot train the model every day to kind of figure out, oh, these new people have joined the platform. So we have figured out a workaround for this. I think it's not perfect, but what we try to do is based on the acquisition budget, we get how many new drivers, let's say, are going to join the platform. We take some sort of similarity with those drivers with the existing drivers and try to map it on that front, that how much retention these guys will have, how much trips per week these guys might have. So we have approximated some parts of that, and that also has worked very well actually. But the final prediction goes not only like this, but incorporating the first trips that we might expect from new drivers.
So you do apply incentives to the new drivers as well?
Yes, but we try to map through similarities, then do a LSTM for them.
How did you decide 6 weeks?
How do we decide 6 weeks? Is the business requirement. That's it. Basically, they want to rolling forecast on 6 weeks basis so that they can plan better. They understand the market dynamics changes every 6 weeks a lot. So 6 weeks is a good amount of time to reassess things and decide on this.
How do you measure performance in production?
How do we measure performance in production is basically, it's not straightforward, I will tell you. So one thing we do is we just, based on a gut feeling of somebody, and with this gut feeling, so we are trying to counter human in this case because there is nothing existing currently. So we have run experiments where for some 6 weeks we have a human who is deciding the budget, a system who is deciding the budget, kind of thing, and then we compare what trips we get sometimes from this guy, machine. So we do a switchback kind of experiment in which we run sometimes for with a human for a city for 6 weeks, next 6 weeks something like that, next 6 weeks something like that. But obviously we do take care of seasonality and other things that comes with this kind of setting, but that's how we try to kind of capture it.
What was the length of sequence in the previous generation?
What do you mean by length of sequence?
I think that how far for the
Okay. So the question is how far we use drivers data in this case. So initially we started everything starting from 2015. So 2010 is just too far out when we started. So 2015 is a good serving point because this model was more developed in 2017 mid to end. So at least we have 2 years of data for some active drivers. That was good enough.
and how well does it capture the seasonality in case of 2 years?
So it captures seasonality pretty well actually. So we do see spikes when we, like in New Year's or something like that, we do see spikes on the performance overall because it's obviously we have a lot of data in this case to kind of capture that part.
So what steps or process do you follow for validating your prediction to make sure that the model is predicting correctly?
So for the offline evaluation I already talked about. So I think the question is what steps we follow to kind of validate the model that we have. For offline,
At scale maybe, like so with there's some validation probably you do when you're developing it, but at scale, how do you actually at scale when you're using it, how do you validate that the model is still giving you a better result than your baseline?
right. So the question is how do we validate the model at scale as you talked about. I think scale when the model is deployed, the scale is pretty easy to capture in this case because a few things for each city, some city teams plus some finance folks decide the budget currently. Okay, so the tool is accessible by all of them. They can run scenarios on this. Okay, the best way to evaluate this tool is how much trust they now have on machine versus what they have in humans, kind of thing. So as I talked about, we run some experiments in terms of saying that okay, we'll run it with human and then we'll run it with machine and see how it performs on a cycle basis. But I think the overall measure of the system is not MAE, not MAPE, but the trust the finance people now has on the system kind of thing. That is the eventual metric that we look for.
Where do you run your model?
Where do I running model?
Where do you train your model? Where do you run your model? What tool are you using?
Oh, so the question is what tool you have used to run this model? So we have used PyTorch for this. There is ongoing work to scale this model and probably convert it to less heavier version of it in terms of we can optimize this better. But initial model was developed in PyTorch and the prototype and everything, the first deployment happened in PyTorch. If that is a question.
With this model, I mean, for any city A or B, I mean, is the computer actually suggesting to the managers incentives per driver, or is there differential incentives per driver, or is there just an incentive per city, or how is that being applied? I mean, or are they taking those recommendations by the model into account and then they are deciding on it, or are you having some cities run on its own automated way that the model itself is pushing those incentives up?
So the question is basically how do we decide on the budget? Is it on a per driver basis or on a city basis? So the good question. Actually, in this case, we cannot do a differential pricing or differential incentives, and that is just not right for drivers. I think the overall idea is we decide for a city. We have a smart way of mapping city level incentives, let's say for driver level incentives. So I've not talked about that in this case, but we have some way, let's say, to map those city level incentives to driver level incentives, and then we use that driver level incentives to do this modeling. Now there is obviously error propagation because that will not be perfect, but I think when we tested our model it was kind of fine. But for city teams, they only care about city level incentives, they don't care about driver level incentives.
Something I saw in the slide instead of predicting just one value, you predict two values, so parameters in the distribution. Have you seen other examples of people doing this?
Can we see what?
Have you seen other examples of people doing this?
So the question is, we are predicting a distribution rather than one value. have we seen other examples of people doing this? I think I don't know the application, but on the research side, if you just see, there are a lot of papers. It's just one way to achieve uncertainty into the predictions. So the many papers just talk about one way to achieve uncertainty is just to predict distribution rather than one value. So I think that's where I've seen majorly. From an application perspective, I'm not aware of right now, but there might be some inside Uber also, I think.
So for LSTM2, you said that you feeded the input including the future incentives. So you have, is that part of the training process? You have to retrain every time that you're like kind of predicting for another set of future incentives?
No. So the question is basically for the second incentives that we put into the incentives, budgeted incentives we put into the LSTM2, do we have to train every time we change it? The answer is no, because for training purposes, we use the actual budgeted incentives from history. And for prediction or inference, basically, somebody can put an incentive into the tool and they can see the result. So you don't have to train them. I think that's about it. Okay, cool. Thanks, guys. Thank you.